So today we are very happy to have Nathan here, and he's going to tell us about q-Virasoro. Please, Nathan.
Okay, thank you. So I've been talking to a lot of you here that I met this past month. I think it's in the benefit of everybody that I get a more pedagogical approach to explaining exactly what we mean by q-Virasoro. And so I'll spend most of the time reviewing things that are known and spend a little time at the end telling you stuff that's not known or in progress. So in the context here, very broadly, what do we mean by good q-deformations? To my knowledge, I mean, this question is very broad, very vague, and there's no good, well-defined, definite answer. And here, the approach I'm going to take is to give you an equally vague answer to this. So we'd like a q-deformation of a theory to have two natural vague properties. One is that when you take q to 1, you should recover the undeformed theory. So this seems like almost like a tautology. More interestingly, and equally vague, we'd like the q-deformation to retain some of the original properties of the undeformed theory. So q-deformation should retain some properties. All right. And so in the context that I'm going to talk about, we're going to talk about Virasoro. And so why is that relevant here? Well, the first motivation in our context was that an observation that the energy eigenstates of some integrable system, which is not very important here, but it's the Calogero-Sutherland model. So this describes particles on a circle with long-range interactions, described by some Hamiltonian, which I will not write explicitly, but that the energy eigenstates of such a system are what's called Jack symmetric polynomials. In the theory of symmetric functions, maybe you're familiar with short polynomials. The Jack polynomial is a deformation of these polynomials. It depends on one parameter, which we'll call beta. Depend on a parameter, beta. So that's one fact. And then another fact is that these polynomials actually realize null states of Virasoro. This is done in free field formalism, but you can show that these Jack polynomials are null states of Virasoro. So this is work by Fagan and Fuchs. And so then the immediate question from people in the symmetric polynomial community was that there does exist a good q-deformation of Jack polynomials called the Macdonald polynomials, which satisfies these two broad properties that when you turn off a parameter in Macdonald polynomials, you should recover the Jack polynomials, and that they are symmetric polynomials. So they retain some property, being symmetric polynomials, of the Jack polynomials. And so here, I will just say Jack polynomials have a good q-deformation, according to the mathematicians, Macdonald polynomials. So the Macdonald polynomials depend on two variables, two parameters, which I'll call in this talk Q and T.
Could you try to write a little bit bigger?
Oh yeah, of course. Another motivation came from the work, maybe I'll write here, of Luciano and Fugai. So C also. Luciano. 396. They studied the restricted solid on solid model, RSOS. And a particular solution of that model called, well, the ABF solution for Andrews, Baxter, Forrester in what's called regime 3. But the important thing is that if you study that solution, it has as a dynamical symmetry, actual q-Virasoro symmetry. And so this is an actual, so this RSOS model studies vapor-solid interfaces in condensed matter, so it's of interest. But so just from the perspective of condensed matter, it is possible that q-Virasoro is an actual symmetry of nature. In fact, it was realized in '96 as such as a dynamical symmetry. And so what do I mean by q-Virasoro here? Well, the question that these authors asked, Shiraishi, Kubo, Awata, and Okada in '95 was, if the Jack polynomials realize the null vectors of Virasoro, what do the Macdonald polynomials realize? A natural guess would be that it should be null vectors of some more general theory, and so they wanted to call this q-Virasoro, and that's how they defined it. And so here, Macdonald polynomial should be, could be. The surprise is that it works. Null vectors of q-Virasoro, whatever that is, and they defined it that way. The surprise is that a year later, the exact algebra they constructed based on these principles was realized as an actual symmetry of some in condensed matter. Yeah.
So maybe you will explain this, but should I think of Q for the purpose of this discussion as a real number, a phase, or something else?
Here we'll take Q and T to be complex.
So no particular.
No. In fact, we'll give arguments from gauge theory later that you should really think of them as some complex numbers. We'll give a gauge theory origin of this construction, which is more the modern perspective. Okay, good. So when I say q-Virasoro, it's a bit of a misnomer. I should really say qt Virasoro based on what I said. And then when you take t equals q to the beta and q to 1, you recover Virasoro with central charge determined by beta. So that's the usual beta that people study in Virasoro. I mean, I'll give explicit formulas later. That's the limit. It's the same limit from which you recover Jack polynomials from Macdonald polynomials. That's why it was initial interest. And then, so it was mostly just based on studying integrable system, the CS model, and understanding exactly how, what its symmetries. So now let me tell you how you construct q-Virasoro. And the definition is in something called the free field, sometimes called Coulomb gas, sometimes called Lutsenko-Fateev. Formalism. The community that cared about this question was almost exclusively Japanese and Russian. So this will be like 99% of the names I'll mention will be Russian or Japanese. And then it got a bit broader, but that's the idea. So what do? You start with a deformed Heisenberg algebra, which I'll write H qt of A1. with generators alpha k that obey the following commutation relations. Alpha k, alpha m, k, delta, and the q deformation enters here. So these might look a little bit scary, but don't worry, we won't actually use them much. And you use these generators to construct screening charges. Let me just construct screening.
So here's, sorry, no, Q and T are just numbers here, right?
That's right.
So if I rescaled this, this would just be standard. If this is the only formula we have, we could get rid of it by rescaling alpha, the alphas. Or is that wrong? Because of the delta Km, it looks like it's correct.
This delta Km might spoil the rescaling. Well, you want to just rescale by this overall factor here.
Square root.
Yes, square root.
So I'm sure it would mess up other things, but just this formula by itself, the deformation wouldn't have much context.
Right. Yes. Maybe when I write down the definition of the screening operators, it will be clear that like this, such a redefinition will not work. But at this level, yes, it seems like you could just rescale.
But the right-hand side goes to 0 when q goes to 1. No?
Sorry?
Yeah. So the right-hand side goes to 0 when q goes to 1.
When q goes to 1, the right-hand side goes to 0. That's right.
So this reason. So there's a subtlety in the rescaling argument.
There's right. Well, yes. Well, yes. So there's many subtleties in the rescaling, and so here let's just take as a definition to define this like this without rescaling and see what that gets us. Screening charges. I'll review what these words mean in the context of usual Virasoro in a second, but well, screening currents will be defined as the integral, screening charges will be defined as some integral of screening currents defined with some contour, where the currents will be some normal ordered exponential, sum over modes, so this is why the name free field comes from. Everything is realized in terms of certain vertex operators, which take the form of exponential of some sum over modes. So this is literally, open any textbook on the Coulomb-Gas formalism, how you construct such objects. Why do you care about these objects? Well, we'll be able to compute correlation functions of, correlation functions in this algebra using this formalism. And that's the only real known formalism that generalizes beyond A1. Now you can replace A1 by an arbitrary simple Lie algebra. This construction works the same way. What you would do is replace this by a version of the Cartan matrix deformed. This you should think of it as when T equals Q as the factor 2, which is the entry of the Cartan matrix of SU2. And so if you replace this factor just by the Cartan matrix of a simple Lie algebra, then suitably deformed, this generalizes to any simple Lie algebra, where you should think of these as root type generators. This again mimics the usual Virasoro construction, where you construct screening currents using roots of the algebra. Okay, so we have a dual set of observables called the fundamental weight unique. So there exists a unique set of fundamental weights The really dual are to the generators that I just defined. And they're defined by alpha, well, I'll call them WK. Okay. And so they're dual because, well, the commutator basically gives you the identity with the roots. This, K, delta K minus M, and the same thing. Okay, so we're almost done. The only thing we need left to discuss correlators is a Fock space representation for the algebra. And that mimics exactly what's done in the undeformed story. So a Fock space. Fock space means you give me, for a given weight psi in the Cartan subalgebra of A1, the Fock space representation is generated by a vector psi such that alpha 0 acting on psi. So this alpha 0 here is the 0 mode I wrote here. I didn't write the conjugate momentum 0 mode. There's also one that should go like log of y. This will only redefine the value of this vacuum. So up to this redefinition, I really don't need. But I'm keeping the 0 center of mass position. Anyway, here, this gives you some eigenvalue. And when you act with alpha k on such a state psi, you should get 0 for k positive. Okay, so far, these are just definitions. And I'll come to why they're the right definitions in a second. Any question on this?
Usually when you define a quantum group, you also need to give a non-trivial coproduct.
Ah, good. There is no such thing here. That will be one of the key part. In what sense is this related to quantum groups? This is essential work by Frankel and Reshetikhin that realize there is a deep relation, and yet there is no coproduct here. And so these are not quantum groups in that sense, and this will be part of where that story became only very recently interesting in a broader context. Yeah, very interesting. Thank you. A comment, you can also construct a set of screenings with the letter T, the parameter T instead of Q. Nothing told me to distinguish them. And that's related in free field formalism to the fact that there's two types of screening currents for Virasoro. And so these are the two types of screening you could find here. You could also use T. In this talk, I'm not going to use the second type of screening, but there's two types of screenings. Let me build a set of operators I'll introduce that will be very important to me in this talk, which are certain vertex operators, which are not screenings, and they're built out of these fundamental weights. So they will do something like, again, a normal ordered exponential. And much simpler here. So just some normal ordered exponential of the sum over modes, z to the k, and some scalar factor that will not matter. It should be here for the definitions I'm going to give. So these are the only operators that I'm going to introduce, and I claim that this is enough to already talk about a lot of physics. So first, maybe let me show you the statements about what is the definition of q-Virasoro. So far, I've only defined a bunch of operators. So definition, this is a mathematical definition. The vector space span by formal power series of the form derivatives of these y operators with respect to z, with some shifts possibly by these two parameters I put in. by A and B are integers, and some arbitrary here derivative. So all power series made up of y operators and their derivatives. Y plus derivative of y plus y inverse. This is allowed to be a negative integer, so plus or minus. So this, with the highest weight specified, that gives you a Fock space representation. This is called a deformed chiral algebra. And so this is a friend called Reshetikin. That's 6. So that's just a definition. So a chiral algebra is actually a pretty complicated object. Just in usual non-q-deformed realm, it has a set of about 7 axioms that it needs to satisfy to be, well, in the theory of, well, a chiral algebra is an object that has 7 or 8 axioms to be defined. And you can formally define by modifying those axioms, again, quite complicated, but you can define properly, mathematically, what it means to talk about the deformed chiral algebra. So this is a well-posed definition. I will not go through the axioms because it will not be of interest for us here, but it's, I can refer you to the original work where you can see exactly how the axioms are modified for usual chiral algebra. And then the definition of q-Virasoro, which I'll call Vir qt, because it has 2 deformation parameters, q and t, is the associative algebra. Subalgebra of the deformed chiral algebra above, which is made of all fields, which consists of all fields that commute with the central charge. So we define the central charge as the integral with a suitably defined contour of the screening current. If you can build all fields that commute with such an operator, these are the generators of qt Virasoro. So that's the definition of what Virasoro qt is. And that definition is true of all q-deformed algebras that are just generalizing to a simple arbitrary, Lie algebra. So if G is a simple Lie algebra, these definitions still work. There's nothing specific about Virasoro. You can talk about W-algebras and W-deformed W-algebras, and there's no problem with that. Any questions? Okay, so let me tell you what happens if I brute force try to construct what operator actually commutes with Q. I've told you what Q is, so let's brute force try to construct, and so I'll give you the answer, and it's an exercise to check, it's a small computation, that the operator I'm going to give you does indeed commute with the screening charge. So let me show you what it looks like. So let's say brute force Q commutes with an operator that I will call T, where T is defined as the Y operator I built over there. This is a certain vertex operator. That's why I introduced it, because it enters here, plus y inverse T over Q. So that's the operator that happens to commute with the screening charge. Okay. So what I mean by inverse here, I literally just mean take the exponential of minus, right? This is all, there's no trick here. So remarks. Remarks. Everything here looks a little confusing. This should correspond to somehow what is the generator of Virasoro? Well, we're looking at the Virasoro stress tensor. This certainly looks very different from the stress tensor in Virasoro. So let me just pause and show you how this happens. So to get back to Virasoro, take the limit t is q to the beta, and q goes to 1. Okay, so what happens if I take this limit? Well, a lot of drastic things happen in the deformed Heisenberg algebra. It becomes alpha k, alpha m is equal to, well, some factor times k times beta delta km, and this is what we call a usual up to rescaling by 2. This is the usual Heisenberg algebra. What happens to screening currents? If you take that same limit, well, you get y to the 0 mode times e to the sum alpha k y k over k. This is just literally the mode expansion of the free boson in 2 dimensions. And so this is how you construct the screening charges. So these are the usual screening charges, at least one set of the screening charges of Virasoro, and the Heisenberg algebra with the modes that these free boson modes should satisfy. So this is we're in good shape in the sense of looks like it satisfies the axioms of what I want by a q-deformation. And we can do better. We can actually make contact with this. And so let me formally do a little bit more refined. T is q to the beta. Take q is e to the h bar goes to 0, and let me expand in h bar. So same limit as here, but let me actually do a Taylor expansion in h bar. And so you find that this operator takes the following form. It's the constant 2 plus this factor, z squared times the actual stress tensor of Virasoro. So this is not at all obvious, but this thing here, can you all see? That's just, well, the usual stress tensor of Virasoro. So I'm really talking about half del phi plus the background charge del squared phi. This operator is what appears here in that limit. When what I call phi is defined by its expansion here in terms of modes, but if you really translate it in terms of, well, this expression, this weird sum of 2 y operators gives you this, plus junk, 1 minus beta squared over 4 beta. So this is at order h bar squared, and then an infinite number of corrections. So to this day, as far as I know, 1 second, it is completely unknown what is the meaning of the higher corrections. So are these higher conserved currents or combination of conserved currents of Virasoro? Nobody has studied this. So this is what is the meaning of the higher corrections? Not known. But it's also not true that just taking this limit, this operator naively just reduces to T Virasoro. it appears at second order expansion in this H-bar limit, but there's a lot of redefinitions and junk to remove if you actually just want to isolate this. Nonetheless, the stress tensor really does appear at the lowest non-trivial order of this expansion of these two Y operators. And you see that structure completely disappears in the limit. You had a question.
No. What do the operators W become in this example in this limit?
The generators W, just like the alphas stay alphas, the W's become literally dual. So I mean, here you're going to get a commutation. They're defined by this commutation relation with the generators alpha. And so you just get commutative alpha with W is, well, K times beta times a delta function. So
the W's are basically like the alphas. It's just a different normalization.
that's right. That's right. Exactly. In the q-deformed context, it's very useful to introduce the two sets because, I mean, some operators only depend on the W's, whereas the screenings only depend on the alphas, which is why these are called root types operators, whereas these W's are called weight type operators. But the distinction is completely meaningless in the limit. Okay. Yes.
Is it possible to write down the modes of the deformed stress tensor in terms of alphas?
Yes.
Is it the same formula or is it the?
Well, it's going to look like an expansion of, in terms of, well, we have to expand this. And then another term that looks like the inverse of this. It doesn't gain you much. Now, Frankel and Reshetzikin made a crucial observation. In the q-deformed context, they recognize here what looks like the fundamental character of SU2 in some operator form. So let's just give you an idea of what I mean. So crucial observation, maybe here I should say 97. Oh, maybe 95. I don't think. In 90, I'll have to check, but it's plus or minus 2 years. But in 97, they realized that T of Z, so Y plus Y inverse, Z times some factors, this looks like an SU2 character. And I'm being very broad by what that means. They developed an entire theory called the theory of Q characters to make sense of this. This was one of the great achievements in the representation theory of quantum groups, that such objects can be constructed. So it looks like an SU2 character, and what I mean by this is just if you take SU2, remember that Y plus 1 over Y is just the spin 1/2 character for the spin 1/2 representation of SU2. Now you can do more interesting things. You can fuse these operators, TZ1 times TZ2, and then you can build tensor products of such representations. And so there's a sense in which this really has to do with some invariant character theory. And so Frankel and Reshetzikin made this rigorous statement. So the actual statement is that for T equal 1, so this is where they developed, they call Q characters because they set T to 1, they keep the Q parameter. Q characters are homomorphisms from the representation ring of UQ A1 hat. So the quantum affine algebra of affine A1. You can substitute your favorite Lie algebra here, simple Lie algebra. The construction still carries through. You just construct the currents that commute with screenings by this requirement, and all such guys realize a character. And so Q characters are homomorphisms from the representation ring of this funny looking quantum algebra to a polynomial ring in y variables. Some Laurent polynomial in y variables can be, so q characters, to say it simply. There's something called quantum affine algebras. You can consider the representation of such guys for finite dimensional irreducible representations. This is a well-defined problem. What is the tensor product? What is the direct sum of such representations? So Frankel and Reshatsikin tell us that you can translate these questions by just multiplying T operators or fusing them, so multiplying y variables, that's tensor product of representations, and adding them, or y inverse or whatever, that's direct sum of representations. And so what we're finding here is something slightly more general that depends on two parameters, T and Q. And so that's why sometimes in the literature they're referred to as QT characters. And they've been repopularized in the, so Frankel and Reshatsikin, furthermore, in '98, constructed these characters with two deformation parameters, which is exactly what we constructed here for Virasoros. And so they thought of these as interpolating between two different quantum groups. Interpolate between UQ of A1 hat representations and UT of Langland's dual, which in this case is just A1, so it's itself. But for quantum affine algebras, they thought, well, we can use these characters. When I set T equal to 1, I end up talking about representation theory of these guys. When I set Q to 1 and T arbitrarily, I end up talking about the representation theory of this thing instead. And so they thought of it as a character interpolating between representation ring of this quantum affine algebra and this. This big U symbol is called the enveloping algebra. Do you want me to explain what that is? Or, I mean, just take it maybe for now that this is called the universal enveloping algebra. And so that thing is what you quantize in quantum groups. You can't quantize G, you have to quantize the algebra, the associative algebra that you build, infinite dimensional, built from G. G is a subalgebra of this. There's an entire theory of that. I'm not going to delve into it. But you have to know that this is where quantum groups make an appearance for the first time. Okay? This is just to tell you. Now, finally, we have like a quantum group that shows up. Okay. So what I wanted to tell you about, and I'll switch gear. Gauge theory. So to understand further the symmetries of this QT deformed Virasoro, one natural thing to look at is the word identities. So word identities. Which look like T of Z is regular in Z. So this again mimics what you would do for usual Virasoro. You consider correlators, insert the stress tensor and ask, well, what is the associated symmetry? This is a word identity. So here, what do I mean by bracket, bracket? Right, so this thing really stands for psi prime, a bunch of vertex operators times product of screenings times the stress tensor. So that's what I mean by correlators. what type of vertex operator you put here crucially will will determine different types of theories from the point of view of what I'm going to talk about later. I'd rather not talk about the vertex operators precisely that I'm going to put here. But if I don't put anything, this is just screenings with T. But if you want to characterize it, put interactions, particles that do interact with some potential, you need to put extra vertex operators in here, and that constrains the symmetries of that theory. So some regularity properties of this correlator can be computed. Why can we compute this exactly? Because we're in free field formalism. Everything's just a bunch of normal ordered exponentials, and so by weak contractions, you can literally just compute such things. Maybe let me just show you for pedagogical purposes how that works in practice. As an example, so use weak contractions or Wick's theorem. So example, just to get an idea. What is the 2 point of two screenings together? Right, so this is just an exercise, very elementary exercise where you literally stare at the formula and compute the 2 points, and you get something that can be expressed as in terms of q-Pohammer symbols. So the bunch of ratios, which are shifted by t here, okay? And then the same thing with the inverted variables. So what do I mean by these symbols? X, Q, infinity, is product of 1 minus Q to the K X. This ratio of q-Pohammers is just a bunch of infinite products. Let me show you that this makes sense. Again, this might not be obvious, but I'm going to do exactly what I did before. Let me take first the q, t equals q to the beta parametrization. So what is this equal to? If t equals q to the beta integer, you don't have to take beta integer in general. You have to analytically continue out of that value. But if you take beta integer, this is equal to the product, to simplify, 0 beta minus 1 of 1 minus q to the k, 1 y2, 1 minus q to the k, y2 over y1. This is just a simplification of this parametrization if beta is an integer. And so this is maybe in matrix models. This has a more famous name. This is the Macdonald measure. Now, if I further take beta equals 1, then you recover 1 minus y1 over y2 to the beta, 1 minus y2 over y1 to the beta. And that's just the measure for beta deformed matrix models. This is the beta ensemble von der Monde determinant, which makes sense. I'm looking at 2 points of screenings. This is what gives the von der Monde in free field formalism. If you further take beta equals 1, you literally end up with the von der Monde for unitary matrix models. That's why this is related to Schur polynomials. This is related to Jack polynomials. This is related to Macdonald polynomials. That's an example of the computations you do. And so you can do all of them just by weak contractions in that way, evaluate exactly what these correlators are, and they all give such expressions.
There you have q equals 1, right? In the last arrow.
Q is 1. Thank you. Yes, sir. Good. Any questions? Maybe that helps getting a bit of a feel for what q-deformed means. Okay, so let's see. Okay. Very roughly, I'm going to tell you how this was rediscovered 15 years later by Nekrasov, Pestun, and Chetashvili in a completely different context, where they were looking at gauge theories, and they realized that these characters that we constructed, these qt characters, are actually objects in gauge theory. They realized partition functions of gauge theory on a funny background called the omega background with certain defects. And so my interest tends to align with supersymmetric gauge theories with certain amount of supersymmetry. And so this is why this is a very nice area to tell you about. But of course, I'm going to be very, very, very broad because we don't have much time. And this would take us way too far now. But the program was initiated formally by Nekrasov in 2015 in a context called the BPS-CFT correspondence. He was trying to match correlators in CFTs to correlators of BPS observables in gauge theory, roughly. That's the program. AGT is an example of that. The AGT correspondence matches uvial conformal blocks to partition functions of four-dimensional gauge theories with 8 supercharges. This is a refinement of that. There's a quantum deformation of this whole correspondence. That's what I'm talking about right here. So roughly, the idea was that, well, example one, I'll give you 2 examples. You talk about 4D Yang-Mills, and you look at the correlators in 4D Yang-Mills. They're defined as a bunch of operators. Roughly, that looks like the integral over some contour with some measure. E to the -1 over h bar action. Operators. All right, so the problem he was interested in was, I suppose I want to vary the fields slightly. I take phi to phi plus delta phi, infinitesimally close, and I ask, what are the symmetry? If I require the correlator to be invariant, or the action to be invariant under such a shift, and provided there's no anomalies, so that the measure doesn't actually change when you've changed phi to phi plus delta phi, what can I learn about the symmetries of the underlying theory? In this case, maybe 4D Yang-Mills. The contour change, so in general, in classical mechanics, when you do this procedure, you land on the Euler-Lagrange equations. This is literally finding the saddle point of the path integral. In quantum mechanics, you don't have that luxury, and you end up with word identities that must be satisfied by such correlators, right? So instead of shifting phi plus a little phi away, you can switch the contours from maybe this contour plus a slight change of contour. And the contours that Nikita cared about were contours that take you from some, well, the connected components of the space of gauge fields are labeled by a number, an integer, called the instanton charge. So the question Nikita was asking was, what if I start in some instanton sector, slightly shift the contour in such a way that k gets shifted by some discrete number, maybe 1. So in general, this is not something you can do. You cannot actually change the contour and ask, well, what are the word identities satisfied by this contour change?
You mean the contour in C2? Oh, no, sorry.
Sorry, the contour gamma.
The path integral contour.
That's right, the path integral contour. So it's defined to, well, in this path integral, I'm in some gauge sector with instanton number k, and I want to shift the contour slightly in such a way that k goes to k plus 1. Which is, well, this is not a, well, this is a well-defined question in a very specific background that Nikita studied called the omega background. Very roughly, let me tell you what that background is, and I'll give you the result of this investigation.
Is the original contour supported on all negative components?
Yes, I would say so. So what is the, well, instead of 4D Yang-Mills, it's better for our purpose to think of this omega background as a fibration of C2, a C2 bundle fibered over S1, a circle of radius R. And so the way this works is that if I start with C2, this is where Yang-Mills live, and I move around the circle by one rotation, abstractly, C2 has rotated with identification QZ, TW, R. So Z is a coordinate on the first C, and W is a coordinate on the other complex line. And so after I rotate by R, the omega background really is cleanly introduced in this 5-dimensional on a circle formalism, where as you go around the circle, you identify C2 with this new C2 that has been rotated independently, each C, by Q and T. These, and this was a realization of our work and of Nikita's work back then, these Q and T's have to do, and in fact, we will see they're identical to the Q and T of Virasoro QT. So questions about symmetries of Virasoro QTs, such what word identities are satisfied, can be recast in gauge theory. Here's the example of maybe a 5-dimensional on a circle. You can also do something in 3 dimensions on a circle. So example 2. Example 2. Consider 3D, maybe any. So first ingredient that was important is that this omega background exists. Second ingredient that's important is it's not just 4D Yang-Mills, it's 4D Yang-Mills with n equal 2 supersymmetry. So that's also important in the construction. Now I can perform localization with respect to the equivariant parameters Q and T and all the fugacities that I have in the problem. But before I go to example 2, maybe let's just finish here. So we're in 5 dimensions on a circle. Instantons are point particles. They are the origin of C2 and they wrap the circle. I want to study the quantum mechanics of such instantons, right? So quantum mechanics of instantons on the circle.
Which gauge groups do we consider?
In this case, any UN, but this construction generalizes to any ADE quivers with unitary gauge groups. Unitary is important because we're doing a non-commutative deformation? Yes. So these are this will realize the moduli space of non-commutative instantons. Yes.
Are we also rotating in R symmetry space or just in physical space? Did we go around the circle?
Yes, so the R symmetries will also, yes, precisely. And so, I mean, which, yeah. Good. And so, okay, this is just a setup that's old and well known. I want to say in the, well, it has 20 years, maybe 15 years, this was introduced. And now the question is, if I want to introduce this setup, where I change the instanton number by 1 unit, so in this setup, point-like instantons at the origin of C2 are the only instantons that contribute in the path integral. Okay, this is a feature of this omega background. All other instantons, what is IR and UV divergences in the instanton moduli space in usual Yang-Mills, but you cure them with this background. The IR divergences are cured, and now you only care about the contribution of singular instantons at the origin. And by equivariant localization, you can compute the partition function of such instantons as a Witten index. with an index, which looks like a trace of -1 of the fermion number times a whole bunch of fugacities with chemical potential turned on for everything that commutes with the superchargers I'm using to compute the index. I'm not going to give the explicit formulas here because this would be, it's pretty lengthy. Now, if I want to realize the instanton shift, I introduce a defect that in some sense mimics the string theory construction. So in string theory, instantons can be thought of as D0 branes embedded in D4 branes. And I change the instanton number in string theory by pulling out D0 branes or adding D0 branes on a D4 brane. And so here, I need some defect that mediates the change in instanton number in gauge theory. So the correct defect here is a Wilson loop, it turns out, wrapping the circle. And that sits, so Wilson loop can be introduced that wraps the circle here and sits at the origin of C2. And so the instantons can interact with the quarks that live on this Wilson loop. And you can couple the bulk to the defect Wilson loop by introducing maybe some extra Fermi multiplets, some fermions in the quantum mechanics. But this is a story that's well known, that you can introduce extra fermions that couple to the bulk and that realizes the degrees of freedom. Well, it couples the theory to the loop. So that's actually that. So the setup is to compute the quantum mechanics of instantons on this funny background with a Wilson loop included that mediates changing the instanton number. And so precisely when I say Wilson loop, a Wilson loop is defined by, well, the path it takes. I told you it wraps S1, and also the representation in which it transforms. In this case, equivalently, what is the representation? The fermions that realize the loop transforming, take them to be the fundamental representation of UN and to be singlets on the, well, let's just say fundamental representation of UN. So if you take this data, you can define the index. It's a 1D n=4 quantum mechanics. Reduction of 0,4 from 2D to 1D. So 2D to 1D. n=4, and you can compute it exactly. And what you find is that the answer for this index takes the form of a correlator, exactly the correlator I wrote before. It's exact QT correlator of the Virasoro if I take this to be U2. Oh. If I take this to be, well, there's some caveats for what the gauge group is, but this ends up giving you like this ends up giving you a QT correlator. So this is what I wrote before with some vertex operator times screenings. Well, I'll just write them as like a bunch of screening charges. So these are where the contours of integration show up in the QT-UV. So the lesson here is that intrinsically, QT-Virasoro is related to, in gauge theories in a higher dimension, what we call the omega background. That's a given. The two parameters of deformation are very natural now because in 4D Yang-Mills, I have two deformation parameters, epsilon, well, Q and T, for this omega background. So it doesn't really make sense to just consider one. You can really just turn on both and ask, what do you get? And so in the CFT language, it's like saying, well, why stop at Virasoro? QT-Virasoro is some natural thing. But then there's many different limits you can take here and ask, what do I get in gauge theory and vice versa? So that's an entire research program. That's just to give you an idea of the type of computations we're doing here. And so the fact that this is regular in Z, this is a worded entity, means that this index has some regularity properties in a variable as well that I'm going to call, well, Z. What is Z? Z is the fermion mass. Fermion mass Z. Complexified because I'm on a circle. So it's a real mass of fermion, but because it's 5D on a circle, well, you complexify this to become, well, this is Z as a complex parameter. And so the fermions that couple the Wilson loop to the bulk call their mass Z. And so the index is a regularity statement about the mass that these fermions should satisfy. So here, this is the position of a vertex operator called the deformed stress tensor on a Riemann surface of genus 0. There, it is the exponentiated mass of a fermion. Okay? There's a full dictionary. The rank of the gauge group is related to the vertex operators that I put here, and so on. You have 5 minutes left? Okay. Yeah. So a second example would be to study 3D n equals 4 or 3D n equals 2 theories also on a circle. Radius r times also an omega background exists. Again, the omega background does the same thing. It rotates a C line, only one C this time, by a parameter Q. And in this context, you can ask, well, what about maybe the vortex number? So let me take the C here is transverse to the circle. So we have an integer called the vortex charge into the gauge linear sigma models or 3D on a circle. And let me ask what happens when I change the vortex number. Right? And so it's exactly the same setup as instantons in 4D or 5D on a circle. Here I'm asking what happens when I change the vortex number. I could have also done that in 4D, but let me like simplify and say in 3D, and then you can define again an equivariant k-theoretical index that defines the again a trace of -1f times a complicated expression that defines the counting vortices coupled to some defect. The defect in this case is not a Wilson loop, it's a vortex loop. So the vortex loop in this case preserves, well, so I still get a quantum mechanics on vortices, quantum mechanics on vortices, so 1D. And so it's 1D n equals 4, but this time it comes from reduction of 2D 2,2 and not 0,4. What the vortices preserve is 2,2. Anyway, so the detail, but introduce a defect, let the vortices couple to the defect and leave the bulk gauge theory. You get an index that ends up being, again, a q-Virasoro correlators. So this is for a 3D UN gauge theory, say for, let's me say if I do 3D n equals 4, it's UN with NF flavors.
What's T now?
Very good question. So T is no longer a geometric parameter that is the omega background. T requires a completely new interpretation. So maybe I'll write it here clean. So T is the twisted mass for the scalar in the adjoint chiral multiplet that sits inside the 3D n equals 4 vector multiplets. So maybe let me just give you the precise dictionary and I'll end here. So in this context, say, I'll end with this example too. So 3D n equals 4. UN with NF fundamentals. So take the vertex operators to be what's called fundamental operators. So literally, g of x equals x to something times e, so that's the zero node, minus some. So some vertex operators that happen to look like this. These are new, I didn't write them before. So say you introduce these vector, those vertex operators inside your correlators. Okay, so these are called fundamental because when you take the T goes to, the unrefined limit, you turn off the q-deformation, this is what is a simple boson vertex operator in usual UV. So if you put these vertex operators in this correlator, then you have a dictionary where Q is the omega background, T is the twisted mass complexified for the adjoint chiral scalar. The correlator has this state psi defined for the Fock space. And so the eigenvalue when alpha 0 acts on psi, remember that this gives you the highest weight value of this. So this parameter, that's the 3D Fi parameter, Bayer-Dupulos, complexified. Because again, we on the circle term. And Z is the mass of the chiral fields, of the chiral field of the defect vortex. The n of UN, that's the number of screening charges you have. And the NF, fundamental hypers of the 3D equal 4, that's the number of fundamental vertex operator you insert. So there's a complete dictionary between, very explicit in 3D here, between these things and these things. So QCFT correlators really completely characterize and have some intrinsic thing to do with supersymmetric gauge theories in 3 dimension on a circle. So always on a circle is important with this Q deformation. If you turn on the Q deformation, you land in 2D theories on the gauge theory side, and some new type of algebras that have recently been defined that are like some reduction, additive version of these multiplicative algebras I define here. And then you get contact, you make contact with Yangian symmetry as opposed to quantum affine symmetry. And as a last comment, there's 2 very interesting directions that this is taking. One is to realize that this is not really a coincidence because, well, there's an extension of, well, thinking of correlators in the q-Virasoro world. Maybe I'll just write it down. Conformal blocks of q-Virasoro are in 1-to-1 correspondence, and that's a conjecture, but there's some few checks now, with the quantum affine A1. So this is better than what I told you before. Before I told you, think of characters here as interpolating between certain algebras at critical level. Here I'm telling you there's an isomorphism of conformal blocks between these 2 theories, and that goes under the name of Q. It's some version of what you can define as Q quantum geometric lengths. So that's work by Aganagic, Okunkov, Frankel, and the dictionary is expanded. You can introduce study line defects, surface defects, a whole bunch of things, and there's a dictionary in here. Another direction of research is to understand better the representation theory of these guys, the deformation of the representation ring of these quantum affine algebras tells you about these things. And finally, one last direction that's very prominent these days is to study an algebra that does have a coproduct in a quantum structure and contains this. And it's called the quantum toroidal algebra of GL1. So that seems to be the natural language for where a lot of these correspondences and results take place, is in this more general algebra. Now, I don't need to tell you the more precise thing, but that's just to give you an overview of the field, the old results, and the more newer stuff that has to do with realizations from gauge theory. This is important. Thank you.
Questions?
related to this AGT relationship?
Yes.
It also involves some Virasoro,
Yes.
some gauge-theory.
Absolutely. So forget T. Just consider correlators with vertex operators and screening charges. These are the conformal blocks of the Virasoro QT algebra. And so these correlators realize partition functions much more simply of what I said here without these defect loops. Just the partition function on this background of the supersymmetric index, computing the index of the instanton quantum mechanics, non-commutative instantons in this omega background does realize correlators, just the correlators without stress tensor insertion, so the conformal blocks of this funny algebra. This is not the uplift of AGT to some extra deformation. This is a different correspondence. It's a dual AGT. If you do the string engineering of these things, it corresponds to some kind of fiber-based duality of the AGT setup, where instead of considering conformal blocks in one channel, you consider them in a different channel. And so it's a rotation, it's an S-dual frame in 5 dimensions, of what I'm talking about. So that's how it relates to AGT. Now, AGT has a 6D origin, which is the 6D 2,0 theory compactified on a Riemann surface, which is a sphere with punctures. In this setup, the origin is the 6D 2,0 little string compactified on a Riemann surface, which has to be genus either 0 or 1, because you need to have a flat solution of type 2B string theory. And in this case, it's the cylinder. So really how you think about it is you have a cylinder, the two ends here characterize the state psi and psi prime, and you put a bunch of vertex operators. So these are the vertex operator maybe that I call V of X from this board, and these are the screenings. So you just put a bunch of those, compute the conformal block. This is an index of the gauge theories we talked about without those Wilson or vortex loop defects. And that the origin is the compactified 2,0 little string on a circle, which is the T-dual circle of this circle. Well, yes. Or the 1,1 little string on this actual circle. Same thing. There's a T-duality of little string, which exchanges the 1,1 on this circle with the 2,0 compactified on the T-dual circle. So there's a complete dictionary there. It only works in, well, so when you take the limit, you can ask, like, let me remove the Q deformation. What do I get? Well, you get a sphere with 2 punctures. By the way, in the q-deformed world, the cylinder is not equivalent to the sphere. They're not conformally equivalent. QT Virasoro does not have conformal symmetry, and Virasoro is not a subalgebra of this deformed Virasoro. And so you really need the cylinder here. It's not a sphere with 2 punctures, it's not the same. But after you turn off the deformation, you can think of this as a sphere with 2 punctures at the end and a bunch of punctures here that are realized by, in the 2,0 little string, by a bunch of D-branes, or in this context, by a bunch of vertex operators in screenings, in free field formalism. Yeah. And you can prove analytically this version of AGT. It's a proof. And you do get correlator equals index to all orders. You don't need, there's no expansion on both sides and matching. So in that way of looking at it, this dual channel, sometimes in integrable system, it's called spectral duality of exchanging momentum and position. So this different S-dual channel of looking at it, where this algebra naturally arises, you can prove the exact statements. That's kind of a surprise.
All right. If we have no more questions, let's thank Nathan again for a very nice talk.